All right, welcome everybody. Today we're going to talk about lesson number 72. This is our final section from chapter 9. This is section 9.5, the binomial theorem. Just a quick note about chapter 9 overall. Sections 9.1 to 9.3, those were all about sequences and series. Section 9.4, we're going to skip altogether because we don't need it. And it's possible we might come back to 9.6 and 9.7 later in the year if there's time. But for now, we're going to go ahead and end it with 9.5. The binomial theorem is something that you might have seen last year in Algebra 2 Honors, or perhaps you've seen somewhere in your SAT studies. The truth is, it's not really my favorite section, and it might not be yours either. But the good news is it's very formula driven. So as long as you follow the patterns and the formulas, you'll be good to go. And that should hopefully be even easier given the open note virtual environment. Take a note that homework number 72 is listed there. That'll be the final homework of this upcoming collection. And notice that even though there is a lot of material in this lesson, there are only a few homework problems. So I certainly focused on quality over quantity. So you'll want to make sure that you do the same. Because this lesson is a little bit on the longer side, remember we are going to be splitting it up a bit, but just make sure that whether in class or for homework, you do watch the lesson in its entirety. So talking about a binomial, as a reminder, it is, of course, a polynomial that has exactly two terms. Here, we're going to talk about how are you able to quickly find a way of raising a binomial to a power. So basically, if you take a look at this screen right here, it has a couple of examples for you. Obviously, here in the first row, you have something to the 0 with power, which no matter what it is always going to be equal to 1. If you have something to the first power, it's of course always equal to itself. If you were to have this binomial squared, you would do our famous FOIL. And then for anything additional after that, you would have to write out multiple copies. So for x plus y cubed, you'd have to multiply x plus y times x plus y times x plus y. You'd have to start by foiling 2 of them, then multiply times the last binomial. And you can see this obviously gets kind of tricky and kind of obnoxious as soon as you pass to the second power. So that's why if there is a quick, easy, efficient way of doing it, we're certainly going to use it. If you take a look here at the next slide, you can see that I've copied that same pattern over here in the left-hand corner. And there are obviously a lot of observations that you can make about these expansions. So let's go ahead and go through them. So first of all, in here, bullet point 1, in each expansion, there are n plus 1 terms. So something that you want to make sure you remember, it's actually the most common mistake people make, is you are actually starting with considered to be row 0. Because of the fact that we're starting off with x plus y to the 0 with power, that is also known as row 0. So you have to make sure you remember that the first row is row 0, or else your answers are always going to be off by 1. So notice that if you are talking about row 0 to the 0 with power, that's equal to 1, which is just one term. If you have something squared to the second power, notice that is equal to something with 3 terms. So you're always going to have one more term than whatever the exponent is. The second point of order here is the fact that x and y have symmetrical roles. So the powers of x are always decreasing by 1 from term to term, where the powers of y are increasing by 1 from term to term. You also want to start thinking not only of it as x and y, but you want to think of it more as the first quantity compared to the second quantity. If you take a look here at, let's say, to the third power, if you're talking about the third power, the powers of x's are supposed to decrease by 1. So that's why you start with the exponent, x cubed, down by 1 becomes x squared, down by 1 again becomes x to the first, and then in the final term, there's no x there because it's x to the 0. You can see that conversely, the powers of y's are increasing, which means it starts in the first term with y to the 0, meaning there are none there, followed by y to the first, y squared, and ending with y cubed. So please make sure that you know that the x's are always going up, the y's are going down. But again, you want to think of it not just in terms of x's and y, but in terms of whatever is in the first location compared to whatever is in the second location, because it's often more than just x and y. It could be something like 5x, it could be something like x squared, or it even could be something like 3a. So you have to make sure you're thinking of it not just as x and y, but as the first quantity and the second quantity. In number 3, notice that for each of the terms, the sum of the powers is always going to be equal to the exponent. So they're using the 5th power as an example. If you were to write out x plus y to the 5th, notice that at every point along the way, if you add up the total exponents, it should always be equal to whatever the original exponent is. Something to just watch out for here, this works for integers only. So if you were to have fractional exponents, that would not be the case. So please make sure you know that it works for integers only. And then finally, you'll notice in each of the problems that there are coefficients. So how is it that you're able to determine those coefficients? Well, you're going to use something called the binomial theorem. So the binomial theorem says the following: if you are trying to expand something to the nth power, we've already talked about what happens to the powers of x and the powers of y on the previous screen. Now we need to talk about how are we potentially going to find all of those missing coefficients. So the coefficients, turns out they're found by using the following formula. You're going to use the idea of NCR, and that is going to be equal to n factorial over n minus r factorial times r factorial. Please note that in addition to using this NCR notation, you will often see notation that looks like this, with the n value up top and the r value down below. You're going to want to start thinking about those n's and r's in terms of n representing the exponent and r representing the term number. Now, again, this C notation, okay, so we're going to kind of use it to stand for C for coefficient, but you also might have learned it last year as a combination. There are buttons on your calculator that do this for you under the math section and the probability, but you do want to make sure that you can do it old school as well. So I'm going to show you how to do it longhand, and you should obviously make sure that you're able to do that. So again, the whole reason why you have to use this formula here is because you need to know what are the coefficients of your answer now that we know the pattern for the x and the y. So here in example 1, they have done some for you, so let's go through them. So here in the right-hand corner, again, there's the formula. That's the formula that I'm using all the way through. So here in example A, they're talking about 8C2. So if they're talking about 8C2, that would mean that n is equal to 8, and that would mean that r is equal to 2. So according to the formula, you're going to do n factorial on the top. You're going to do n minus r, which would be 8 minus 2, which is 6 factorial. Then you're going to multiply it by r factorial, which is, again, 2 factorial. The whole reason why we spent some time earlier in the chapter simplifying was because now you want to try to reduce. So think about what would happen if you were to take the 8 factorial on the top and multiply it all out. If you were to take the 8 factorial and separate it into something that's common with the denominator, you could take out 6 factorial, which would leave you with just a 7 and an 8. This 6 factorial would cancel out with this 6 factorial. All you'd be left with on the bottom is 2 factorial, which is 2 times 1. And if you go ahead and simplify 56 divided by 2, that's how you get a final answer of 28. Now that 28 actually means a lot of things, which we're going to see as the lesson progresses. But for now, we're going to think of it as being the coefficient of that binomial expansion. 10(3). So again, using the formula, it's 10 factorial over 7 factorial times 3 factorial. If you were to look at 10 factorial, you could take out a 7 factorial, then reduce that with the 7 factorial on the bottom. All you would be left with on the top is 10 times 9 times 8. All you would be left with on the bottom is 3 times 2 times 1. If you then went ahead and simplified that, you would get a final answer of 120. So again, if you're thinking of the n as being the exponent and you're thinking about the r as being the term number, we're going to be able to use those to find values if we know all of them. Here in C, so 7C0, pay attention here. What's going to happen anytime you have a 0 over here in the R slot? When you have a 0 in the R slot, the factorial on the top is always going to cancel the factorial on the bottom. 0 factorial, in case you forgot by definition, is always equal to 1. So anytime you have a 0 in the R slot, you're always going to get a final answer of 1. And if you can just remember that, you don't even have to show any work. Similar pattern for D. So in D, you're assuming that n and r are both equal. If n and r are both equal, you're again always going to get a factorial that cancels. Then 0 factorial, again, by definition, is only just 1. So you're going to want to make sure that you remember that if you have the same n and the same r, that always cancels to be 1. And of course, if you forget, you can always just use the formulas. Now let me show a couple all the way through just in case. So 9C2, again, we're going to be using the formula here. So if you're using the formula, you're going to go ahead and identify n as 9 factorial over 9 minus 2 is 7 factorial, 2 factorial. If you were to go ahead and think about 9 factorial, how could you possibly get 9 factorial to reduce with 7 factorial? Well, if you took out the 7 factorial, you just would be left with 9 and 8. And then 2 factorial is, of course, 2 times 1. Cancel those 7 factorials. That's going to give you 72 divided by 2, which is going to give you a final answer of 36. 11 over 4, that's going to, and again, inside those parentheses, not a fraction. It's, 11 is the n, and then r is the 4. So that is going to be equivalent to 11 factorial over 7 factorial, 4 factorial. You're again always trying to cancel out the larger factorial from the bottom. So if you were to think about a 7 factorial out of 11 factorial, okay, you would be left with, of course, 11, 10, 9, and 8. That would cancel with the 7 factorial on the bottom, leaving you with 4 factorial, 4 times 3 times 2 times 1. If you go ahead and multiply 11 times 10 times 9 times 8, that is going to give you 7920. If you go ahead and multiply the numbers on the bottom, that's going to give you 24. And if you simplify, that is going to give you a final coefficient of 330. So this formula here that we've been using, super important. Make sure that you write it down and you know where to find it. Here on the next couple of slides, so these are just kind of hints and shortcuts to what I just showed you. You can either use this in lieu of what I just taught you, in conjunction with what I just taught you, or to be honest, if it doesn't really make sense to you, you can kind of just disregard it. What they're trying to show you here is that whatever your value turns out to be here for r, you should always be left with that many factors on the top and bottom, so long as r is not equal to 0, and so long as r is not equal to n. Remember, those are the special cases, which we saw on the previous slide. So here in this example, because of the fact that r was equal to 2, when you simplify the factorials, you have exactly 2 factors on the top and bottom. In the next one, where you have r equals 3, you wind up having exactly 3 factors in the numerator and the denominator. So this is a good way to check. Again, it's also kind of a shortcut. Because this answer is 10, you're going to wind up with canceling whatever 10 minus 3 is, which is the 7 factorial, which is why you're left with just 10, 9, 8. Here, because this is 8, you're going to wind up canceling it with the 8 minus 2, which is 6 factorial, which is why you're only left with 8 times 7, and then 2 times 1 on the bottom. So again, a bit of a shortcut. Take a look here at a couple more examples. So 7C3, if you're trying to kind of simplify that without actually using the entire formula from the previous slide, 7 minus 3 is 4 factorial. If you cancel 4 factorial out of 7 factorial, you're just left with 765. 3 factorial on the bottom, 3, 2, 1. Reduce whatever you can. Simplify to be 35. Then you have 7 and 4. So if you do 7 minus 4, you get 3 factorial. If you cancel 3 factorial away from 7 factorial, you're left with 7, 6, 5, 4. You're left with 4 factorial on the bottom. And if you go ahead and reduce, you're left with your answer. A special note over here, take a look at the fact that A and B wound up being the same. In general, if you're trying to find NCR, it's going to be equal to NCN minus R. So that's how we can see here that 7C3 and 7C4 would wind up being the same. Again, just kind of an interesting fact, perhaps a shortcut for you to use, but if you'd rather just kind of do them all using the formula, that would work as well. In these last 2 examples here, a couple things to notice. One, notice they wind up being the same, and they wind up being the same for the same reason here. They both also wind up being just one term over one term, and that's because of the fact that you have a 1 in this slot here. So again, this is just meant to be a time saver. If you want to see a couple of those time savers in action, let's take a look at example 4. So in example 4, if you have 8 and 3, so 8 minus 3 is 5 factorial. If you were to take 5 factorial out of 8 factorial on the top, you'd be left with 8, 7, 6. If you were to go ahead and do 3 factorial on the bottom, you'd be left with 3 times 2 times 1. If you multiply out the top, you get 336. Multiply out the bottom, you get 6, and that would divide to be 56. Sorry that I don't have my multipliers here. For some reason, when I try to do that, it makes my screen go a little bit wonky. 14C1, again, if you want to think about what 14C1 would look like. So 14 minus 1 is 13 factorial. If you cancel 13 factorial away from 14 factorial, all you're left with is 14. All you'd be left with on the bottom is 1 or 1 factorial, and that would simplify to be a nice simple 14. All right, so the next application of this is something called Pascal's triangle, which is very likely that you've heard about. Thinking back to our good old days at school, there's a big one of these right outside of our classroom. So this is Pascal's triangle, and if you didn't know, it basically is how you can find the coefficients of any binomial expansion. It was named after the famous French mathematician Blaise Pascal. So the pattern here is that the first and last number of every single row is always a 1. And again, please remember, you're going to assume that we are starting at row 0. If you forget that fact, you're always going to be 1 off. Then to find the coefficients in the row underneath it, you are going to add a 1 on the very left-hand side, add a 1 on the very right-hand side, and then add the 2 numbers in between. So if I take 1 to start, I know there's going to be a 1 to start and a 1 to finish. In my next row, 1 on the ends, add 1 plus 1 to get 2. In the next row, 1 on the end, 1 on the end, add 1 plus 2 to get 3. Add 1 plus 2 to get 3. And the pattern obviously continues. Here I've shown you just a couple of rows. You might want to consider writing the first couple of rows or taking a picture of it because you're going to be referring to it again and again. This is showing you how those coefficients now directly relate to the binomial expansions. Remember that when it comes to the x and the y pattern, we already talked about that previously. Now we're talking specifically about the coefficients. So here you can see your 1, your 1, your 1. 1's on the outside, 1 plus 1 is 2. In the next row, 1's on the outside, 1 plus 2 is 3, 2 plus 1 is 3, and again, the pattern continues, and continues. I don't know how many of these you'd actually want to memorize, but it would be a good idea for you to kind of try to get familiar with the numbers, just so it makes it a little bit easier for you to double check your answer. And again, in general, the nth row of Pascal's triangle is going to be equivalent to whatever this exponent is. So again, x is not only going to represent the exponent, but it's also going to represent the row number. And then you're going to see that r is always going to represent the term number, meaning what term is it in the row. So here's an example of a question I could ask you. Use the 7th row of Pascal's triangle to find the binomial coefficients. So again, remember this is row 0, and then 1, 2, 3, 4, 5, 6. That makes this row 7. Notice I'm asking you to use row 7 to tell me things about n equals 8. So I am using this 8 here to represent the row. So I want to know things about the 8th row. So if I want to find things about the 8th row, I'm going to start by putting a 1 on each of the ends. Then to find the coefficients in between, I'm going to add the 2 numbers that are directly on top of it. So if I take a look at this 1 and this 7, my coefficient here is going to be an 8. If I then look at 7 and 21, I'm going to get a 28. 21 plus 35, that is going to give me a 56. 35 plus 35 is a 70. Then notice that the pattern continues. Oh, I lost my 5 there. Sorry. So 1, 8, 28, 56, 70. And then notice the pattern continues again, 56, 28, 8, and then 1. There is a direct correlation between this row and these calculations. So 8C0, what that means is row 8, term 0. 8C1 means row 8, term 1, and so on and so forth. So you want to make sure that you understand that there is a direct correlation between whatever the first number is, that's the row, and whatever the second number is, that is the term number. So this would be 1, this would be 8, this would be 28, and again, the pattern would continue all the way across. All right, so now we are going to use everything that we just went over to figure out how we can actually calculate expansions of things without actually having to multiply out a ton of different binomials. So the pattern for the x's, or again, whatever's in the first slot, remember those are going to decrease by 1. Remember that the pattern for the y's, or whatever is in the second slot, that is always going to increase by 1. Look at the sign in the middle. If the sign is in the middle, that means that when you do your expansion, you're going to get every single coefficient being positive. If you're wondering what happens if it's negative, we'll get to that in a minute. Once you realize what you're doing in terms of the variables, you want to take a look at this n here, and you are going to directly find on Pascal's triangle what row that is. So that 3 is the n, which indicates that we need to go to row 3. Remember that when you're looking at Pascal's triangle, you're starting at row 0. So if you count row 0, 1, 2, and 3, this is row 3 right here. So you're going to copy your coefficients, 1, 3, 3, and 1, all positive, again, because this is a plus. Then you're going to start by taking whatever is in the first slot, which is x, and those powers are going to decrease by 1, starting with whatever n is. So because n was 3, that's how you get x to the third. Go down by 1 to get x squared. Go down by 1 again, which is how you get x to the first. And go down by 1 again to get x to the 0, which is, of course, just 1. Then notice that for the second term, which is just 1, you are going to increase those powers by 1, starting with 0. So this would be 1 to the 0, which of course disappears. This would be 1 to the first, 1 squared, and 1 cubed. Once you realize where all the values go in your final answer, you're going to go ahead and simplify. I think you definitely need to see one of those kind of done together. So let's take a look here at example 7. So you're going to go ahead and find the expansion of x plus 2 to the 4th. So starting with the fact that this is a 4, that's how I know that I'm going to look for row 4. And again, if you're talking about looking for row 4, you have to remember that you're starting at row 0. So row 4 would be right here. So I'm going to go ahead and start by just writing out my coefficients. I know that whatever I'm about to write is going to start with a positive 1. My second coefficient is a positive 4, followed by a positive 6, followed by a positive 4, followed by a positive 1. So now I have to go ahead and take my two quantities, and I have to go ahead and I have to use the pattern. Again, this positive right here is how I know that all of the coefficients are going to be positive. So taking a look at the first term, which is x, whatever is in that slot, you're going to decrease the powers by 1, starting at the biggest. So because n is 4, you're going to get x4, x3, x2, x1, and finally x0. Whatever is in the second slot, that is going to have a power that increases by 1, starting off with the 0th power. So this would be 2 to the 0, 2 to the first, 2 squared, 2 cubed, and 2 to the 4th. And then in your final answer, you want to try to simplify. So 1x to the 4th, 2 to the 0, that just becomes x to the 4th, plus 8x cubed, plus 2 squared is 4, times 6 is 24, x squared, plus 2 cubed is 8, times 4 is 32, x, plus 2 to the 4th is 16. So x to the fourth plus 8x cubed plus 24x squared plus 32x plus 16. Now, if you're wondering, would it really take me that long to do x plus 2 times x plus 2 times x plus 2 times x plus 2? Well, maybe not, but what if you were going to the 14th power? Or what if instead of x plus 2, what if it was 10xy plus 16? Then this obviously is going to be a bit of a time saver. Here's a note, what happens if you are doing a difference as opposed to a sum? So notice that now you're being asked to expand things that are subtractions. When there is a subtraction, you have to alternate the sign. And when you're alternating the sign, you always start as a positive and then alternate to a negative. So start with a positive, alternate to a negative, use the correct row in Pascal's triangle to find the coefficients. And then again, for whatever's in the first slot, those powers are going to go down by 1, starting at whatever n is. Whatever's in the second slot, those powers are going to increase by 1, and starting at 0 up to whatever the n is. So here are 2 problems that are done for you. Again, feel free to pause the video and look at them as closely as you might be interested in. We're going to go ahead and do one together here in example 9. So find the expansion for the expression 2x minus y to the fourth. And again, a little bit of a reminder that you're always decreasing the first value by 1 and increasing the second value by 1. So again, this 4, we're again going to be using row 4. And it's actually kind of a good thing, I think, that we're using row 4 a couple times in a row, just to see how even though you start with the same coefficients, you don't wind up with the same coefficients in the end after you do all of the simplifying. So the first thing I'm going to notice here is that I need to use row 4. The second thing I'm going to notice here is that because it's a negative, I'm going to have an alternation of signs, always starting off with a positive. So I know that this is going to start off with a positive 1. Then I know that I'm going to have a negative 4 coefficient, then a positive 6, a negative 4, and then finally a positive 1. So coefficients come from the row, signs alternate. Then I have to take whatever's in the first slot, and those powers are going to decrease by 1, starting with the highest exponent, which is 4. And in this case, it's not just an x, but it's a 2x. So this would actually be 2x to the fourth, followed by 2x cubed, followed by 2x squared, followed by 2x to the first, followed by 2x to the 0. And, as you get better at these, if you kind of want to be a little bit of a step skipper, that's okay. Certainly, I think for now, it's good to see all of it. Then your second slotted value is just a y here. Remember that the powers of y are going to increase, starting with 0. So this is going to be y to the 0th, to the first, squared, cubed, and to the fourth. And then, of course, in your final answer, you're going to want to go ahead and simplify here. So in your first term here, 2x to the fourth, you have to make sure that you are raising the 2 and the x both to the fourth power. So 2 to the fourth is what give you a 16, and then x to the fourth. Anything to the 0 power, of course, is just a 1. Then when you do 2x cubed, so cube the 2, you get 8 times 4 is 32. Cube the x. And don't forget the y, plus square the 2, you get 4, times 6 is 24, x squared, y squared. Then 2 times 4 is 8, x, y cubed. And last but not least, a positive y to the fourth. Let me double check with my answer key here to make sure that that is correct. It is. And again, something else you want to notice here, remember, as long as the exponents are integers, the total sum of the integers in any step should always equal whatever n is. So here, there's only one variable, 4, 3 plus 1, 4, 2 plus 2, 4, 1 plus 3, 4, and then 4. So that's just another kind of way to make sure that you are, in fact, doing this correctly. Here in number 10, again, is another example that's done for you. It's just giving you a slightly harder version where one of your quantities might have an exponent other than just 1. You have to make sure that you're still raising that quantity to whatever power the step implies. So again, take some time to look through example 10 as long as you might need. I think it's helpful to maybe look together at example 11. Spoiler alert, this is again a row 4 problem, which I didn't necessarily pick on purpose, but again, I think it's, not a bad idea to see how, even though you're starting with all the same coefficients, you're certainly not ending up that way. So here in example 11, notice that I'm using row 4, and then additionally notice that it's a subtraction action, which means that my signs are going to alternate. So I'm going to start again with a positive 1, followed by a negative 4, a positive 6, a negative 4, and a positive 1. Now I'm going to go ahead and look at whatever my first quantity is, 3, and I'm going to make sure that those powers start with 4 and then decrease by 1. So that is going to give me 3 to the 4th, 3 cubed, 3 squared, 3 to the 1st, and 3 to the 0. Then I'm going to look at my x squared power. You have to take the entire quantity x squared and raise it to the power starting with 0 all the way up to 4. So this is going to be x squared to the 0, x squared to the 1st, x squared squared, x squared cubed, and then x squared to the 4th. So let's go ahead and simplify. There in the first term, x's cancel, and you just get 3 to the 4th, which is 81, minus 3 cubed is 27, times 4 is 108, x squared. Then you have 9 times 6, which is 54, x to the 4th, minus 4 times 3 is 12x to, I think I lost my 3 there, x to the 6th, and then finally plus x to the 8th. So again, let me double check that. 81 minus 108 x squared plus 54x to the 4th. Yep, everything looks good. And notice here that, again, so these exponents are not necessarily adding up to be the original n, and that's because of the fact that you had the squared there. So the rules are, of course, a little bit different when that occurs. Okay, so then the final thing you have to be able to do is sometimes I just want you to identify me one specific term from the expansion. So I don't actually want to know the whole thing. I just want to know what one specific term would be. In order to do that, you are going to use this fact right here, the r plus 1th term, and they say it like that because of the fact that you're starting with the 0th row, or n the 0th term, is given to you as NCR, which is the same as it was earlier, and then x to the n minus r times y to the r. So an example of that here in number 12, find the 6th term of a plus 2b to the 8th. So a couple of things that we want to note here. So the fact that we are trying to find the 6th term, again, because of the fact that you're talking about always being one off, if you're trying to find the 6th term, you're going to say that r is 1 less, which is why r equals 5. Again, that's because you're starting at the 0th row and the 0th term. Then the exponent is 8. The first slot has an a in it. The second slot has a 2b in it. So according to the formula, you're going to do NCR, then you're going to raise whatever is in the X slot to the N minus R, then you're going to multiply it by whatever's in the Y slot to the R. 8C5 is equal to 56. There's a lot of different ways that you could figure that out. You could use the calculator, you could look at Pascal's triangle, you can use the formula, which I'm going to show you in the next one, but no matter what, you have to be able to calculate 8C5, then A to the 3rd, and then 2b to the 5th. When you calculate 2b to the 5th, that winds up being 32b to the 5th. And if you combine that with the 56a cubed, that's how you get a final step of 56 times 32 is 1792, a to the 3rd and b to the 5th. So again, these are a little bit obnoxious. I wouldn't ask you to do a ton of these, but this is saving you the trouble of having to do the entire sequence. They just want one particular term. So let's go ahead and finish off with one last example here. Find the 8th term of 4x plus 3y to the 9th. So the fact that you are trying to find the 8th term, remember you're going to always be given that as the r plus 1th term. So your r is always going to be 1 less, which in this case means r is going to be equal to 7. Whatever the exponent is, that is going to be your n. Whatever is in the first slot, that is going to be equal to the x. And whatever is in the y slot is what is going to be equal to the y. So according to the formula, this is going to be 9c7 times 4x, the entire quantity, to the 9 minus 7, times 3y, the entire quantity, to the 7th. Now, if you're trying to find 9c7 without a calculator, you have to go back a few slides to look at the formula. The formula is always the n factorial over n minus r factorial, which would be 2 factorial, times r factorial, which would be 7 factorial. If you think about what would reduce here, if you were to write out 9 factorial, you could take out a 7 factorial, and you would just be left with 9 times 8. And then on the bottom, you would have 2 times 1. And again, that's 7 factorial. So those 7 factorials would cancel. You would get 72 divided by 2, which would be 36. So 36 is equal to 9c7. And again, if you wanted to find that using Pascal's triangle, you could go to the appropriate row and term number, and that would tell you how to do that. So you would go to row 9, term 7, and you should see a 36 there. But again, you have to remember that you're starting counting at 0, or else you're always going to be 1 off. So then this would become 4x squared, the whole thing, which would give you 4 squared times x squared, and then 3 to the 7th, y to the 7th. And so in your final answer, you're going to simplify that whole thing. So you're going to multiply 36 times 16 times 3 to the 7th, which is a huge number, 1,259,712. Follow it up with all the x's, of which there are 2, and all the y's, of which there are 7.